1,3-propanediol is a monomer that is currently produced by DuPont Tate & Lyle Bioproducts, a joint venture between DuPont and Tate & Lyle in a process using corn glucose in Loudon, Tennessee, in the United States. We have derived a black box model for the aerobic fermentation process consisting of three equations: hyperbolic substrate uptake, Herbert-Burt, and QP mu. Four variables, CS, QS, mu and QP, and 7 parameters: QS max and KS for substrate uptake, A, B and MS in the Herbert-Burt reaction, and 2 parameters in the QP mu relationship. Parameter estimation can very well be done using chemostat data on the 4 variables to estimate the 7 parameters. But how many experiments are needed? A minimum of 2 different mu's is required to evaluate all 4 variables and estimate the parameter values. If 3 mu's would be applied, then nonlinear regression is possible, or if the deviations in the regression appear to be very large, then a consistency check is possible to find out if there are measurement errors or perhaps a missing mechanism, such as byproduct formation was overlooked. In practice, in lab research, 5 to 10 different mu's are usually tested to allow precise parameter fitting and have sufficient confidence that the process is understood and under control. Now let a set of experimental information be available for PDO as in the projected table. This can be best accomplished via a series of chemostat experiments, but also could be done using fed batch trials, although the calculations of the Q rates from the primary measurement data will be slightly more difficult. Linear and nonlinear regression on these data yields QS max is 0.2, QS or KS is 0.5, QP is 0.05, multiplied by mu divided by mu plus 0.3. QS is 0.25 mu plus 0.8 QP plus 0.005. And this is the set of equations. The PDO process reaction can be derived from the kinetic and stoichiometric elements of the model using the Herbert-Burt reaction and the QP mu relationship. All other QIs can be derived from the QS, QP, mu rates, including the rate of heat formation using conservation of elements and electrical charge. We need the biomass reaction rate with the rate mu, the product reaction rate with the rate QP, and the maintenance reaction rate with the rate MS is 0.005 altogether. The unknowns can be calculated from the element and the electrical charge balances. The PDO process reaction follows and is only dependent on mu. For the given model, as calculated above, the optimum mu is 0.0245 per hour, where the QS over QP ratio is lowest, and QP is 0.0225 moles P per mole per hour. QS is 0.0291 mole S per mole X per hour, and CS, substrate concentration, is 85 micromoles per kilo. At this mu and using gaseous ammonia supplied via the inlet air, the process reaction reads then as follows. Glucose plus ammonia and oxygen with certain coefficients result in biomass, CO2, water, heat, and 1 mole of product. The process reaction can be used to design and evaluate the inputs and outputs of the process, further using key assumptions on temperature, pressure, and pH, and applying gas and liquid balances, which I will now further illustrate. So let's take a PDO production rate of 165,000 mole P per hour and operate the plant 8,000 hours per year. This results in a production of 100 kilotons per year. A bubble column of 25 meters tall, operated at 1 bar top pressure at 35 degrees centigrade, fed by a glucose syrup containing 3 moles per kilo. One key assumption is further needed, and that is on the off-gas composition. One could, for example, assume a maximum CO2 concentration that does not cause inhibition. Or alternatively, the oxygen content in the outlet gas, YO, out, can be chosen. Here in this unit we assume the oxygen content at 0.0725 moles per mole. This is equivalent to a depletion of about 0.0055 moles per mole per meter height, which is a useful rule of thumb from industrial practice. At 35 degrees centigrade, the water content in the off-gas is about 0.06 mole per mole. Now the design task can be executed. The combined nitrogen, CO2 and oxygen balances in the gas phase result in the total flows of gas in and out of the reactor and the CO2 fraction in the off-gas of 0.1614 moles per mole. The broth glucose balance results in an output flow rate of 71,000 kilo per hour and the total mass balance then an outflow rate of 54,000 kilo per hour. The ammonia balance indicates that about 35,000 moles nitrogen per hour must be sparged, and the other gaseous compound balances in the broth reveal a transfer of 433,000 mole oxygen per hour, 607,000 mole carbon per hour, CO2 per hour, and 225 moles water per hour. Further, the compound balances of cell biomass and PDO give a biomass concentration of 3.275 mole biomass per kilo and 3 moles product per kilo. The total required broth mass can be found from Rp divided by Qp divided by Cx and reads 2,225 tons. Heat removal follows from the heat balance, based on only the mechanisms of evaporation and reaction. The heat to be removed then is about 51,000 kilojoule per hour. All gas and liquid input and output rates, as well as their compositions, can be calculated in a straightforward manner, and thus a rich output is obtained from a relatively small set of inputs and assumptions. And we can also use the model to explore opportunities for strain and process improvement. Upon scrutinizing, we can suggest ways to minimize reactor volume, reduce the oxygen uptake and glucose and ammonia needs, get the highest titer and the lowest cooling requirements. In normal practice, one would concentrate on increasing the QP divided by mu ratio via metabolic engineering or lab evolution. Interestingly, such improvement will also directly result in lower QO and Q heat, allowing capital and operational savings on industrial scale, as well as lower QC, reducing CO2 inhibition risks. The question now would be, can QO be minimized to zero such that an anaerobic process is possible? According to the Gibbs energy calculations, about 110 kilojoule per mole is released, and anaerobic operation would indeed be an option, and research could be well spent in this direction. Another path could be to obtain higher titers via influencing the water balance. A higher QP divided by mu will also result in less water reaction produced. If we could use water-free feedstocks or enhance further the water evaporation rate, for example via a higher broth temperature, in combination with a lower headspace pressure, then such goal could also be within reach. To close this unit, here a final remark on the selection on the right units. All rates and flows are expressed on mass basis, via kilograms or moles, and never on volume basis. This is because volume is not a preserved property, but influenced by temperature and pressure, gas holdup and concentrations. The banana peel is that you use volumes, and then you can easily make big mistakes in the design and operations.